Hello everyone, my name is Violeta Hernandez, and welcome to part 1 of my series on Ordinals and Cardinals. In this series I hope to introduce to you these topics which I have been passionate about for quite some time, and I hope that by the end of it you might share my passion as well. So for today's video I only really have two goals. I would like to give you a broad introduction to the topic, give you a bit of an idea of how the Ordinals and the Cardinals look like, what you can do with them. I would like to give an example of one particular problem where they might come up. And on that second note, I would also like to talk to you about why this topic should even interest you in the first place. So, before going further, I would like to talk to you a little bit about what this series is supposed to be. So, first of all, this is entirely unscripted. I'm trying to go for a more casual sort of vibe here. I basically want this to be sort of like a college lecture where I'm just here at the whiteboard. I'm just going to be explaining things, and I'm going to be going over some rough points which I might take a half hour, perhaps an hour to get through. And on that note, I would also like to emphasize that this isn't really meant as pop sci. There are some great videos out there which go over the broader details of the subject. Visa's video on how to count, for instance, is an excellent example of pop sci mathematics. But my goal here is to be a bit more, let's say, formal. I would like this to be more of a college lecture style of series. So I am going to ask for some prerequisites here, but not very many. I will try to keep this as basic of a level as I can. So we're going to go over proofs. That's the main thing. I am going to prove my statements. I'm going to give detailed arguments for the things that I say. And because of that, if you're not familiar with mathematical proofs, this series might not be for you. I will link other videos on the subject if you're one of the persons who might be interested in learning about the topic of how to do mathematics in general. Now, aside from that, I'm trying to not really ask for anything major. I'm not going to be assuming any knowledge on topics like analysis or topology, though I may draw from them for some examples here and there. And, well, with that said, let's get into the video, shall we? So, the very first thing that I want to do is I want to motivate the problem, right? Because everything in mathematics usually it arises from a need to solve another problem that already existed, right? The natural numbers solve the problem of counting. Well, that's a bit of a funny example considering that that's what the cardinals are going to be doing as well, but I'm getting ahead of myself. The point that I'm trying to make is that we don't invent mathematics out of thin air. We don't create new concepts just because. We are trying to solve problems. And the problem that ordinals and cardinals try to solve is the problem of counting. So let's think of this. How would you count some collection? A mathematician might use the word set. I'll be trying to avoid explicit mention of set theory as much as I can, and there's a reason for this. I'll get to it eventually. But let's just take some collection, some set, some whatever. Let's say we have, for instance, might have the different types of cards, right? I forget the name, but we have hearts, we have clubs, we have spades. I'm trying to do my best drawings here. They're not going very well. And we have diamonds. So we have a collection. And my question is simply, how many things do we have within this collection? And this might seem like an entirely trivial affair because it is, of course. There's 4 different suits, right? That's not really something that takes some genius to figure out. but I would like to analyze the situation mathematically a bit closer. What does it mean to say that there are 4 elements within this collection? Well, one particular way that we can see it is, let's say that we have the numbers 1 through 4. 1, 2, 3, 4. Whenever we count things within a collection, I mean, when we do it day to day, I'm not strictly talking about mathematics here. When we count a collection, we usually go 1, 2, 3, 4, right? To say that there are 4 elements here means that we can do that sort of process. We can match up each of the elements here to a natural number between 1 and 4. To be more precise, the thing that we're doing here is establish a one-to-one correspondence between this collection of suits and this collection of natural numbers, the collection 1, 2, 3, and 4. So, to say that a set has 4 elements just means that it has some correspondence with this set, right? The set of things from 1 to 4. If I had another set, say the letters A, B, C, D, then we can also draw one-to-one correspondence, right? We can match A to 1, B to 2, C to 3, D to 4. Now, it is important to know that the correspondence here is pretty much arbitrary. Like A to 1, B to 2, that might be the more sensible correspondence, because, I mean, we know how the alphabet is supposed to be ordered, right? But we might as well have matched them up like this: B to 1, C to 3, A to 4, D to 2. I mean, the correspondence is maybe a bit, let's say, arbitrary, ad hoc perhaps, but I mean, the correspondence they're all the same, right? We haven't really changed the fact that every number from 1 to 4 corresponds to one letter from A to D. So that means that both collections have the same amount of elements, right? So the idea with the cardinals is basically to take this idea to its logical extreme. Let's say that we have the natural numbers here, right? We have 0, 1, 2. That's an important note, by the way. I am going to be considering 0 as a natural number, and that's going to be quite important later on. So you better keep that in mind. Let's write it until here. Let's put on some ellipses just to show that this set goes on and on. Let's consider a different set. For instance, the integers. The integers are the natural numbers, but they also include the negatives. So when you have 0, 1, -1, 2, -2, and it goes on both directions. Now we might look at these two different sets, and we might conclude that the integers must surely be larger, right? I mean, 0, 1, 2, 3, 4, every natural number corresponds to an integer, and in fact we even have some integers left over. There's no natural number that corresponds to -1 or -2. So it would seem like the integers are a larger collection. And I mean, in a strict subset sense, they are. We do in fact have that the naturals are a subset of the integers. Or if you would like to be a bit more, let's say, inspired by mother in algebra, one might say that you have an injective map or an injective morphism from the naturals to the integers. The point here is that one collection does in some sense contain the other. But let's consider this other thing. Sorry, I shouldn't be deleting this. We can consider a different sort of correspondence, right? And let me just figure out how to erase things in this. I think I'm gonna have to cut the video here. I'll be right back. Okay, So let's consider this other correspondence. Let's say that the number 0 goes to the integer 0. Let's say that 1 goes to 1. And now let's say that 2 goes to -1. 3 is going to go to 2. 4 is going to go to -2. 5 will be sent to 3. 6 will be sent to -3. Let me check. Yeah, this is still visible on the screen. So to be more precise, this function is going to be defined in the following way. We have a function from the naturals to the integers, and I'm defining it so that f of n is equal to negative n over 2 if n is even, and it's going to be defined as n plus 1 over 2 if n is odd. Now it's pretty easy to check that both of these are going to be integers. Now you can also check, and this is something that you can do in your free time, you can pause the video and try to convince yourself of it, that this is in fact going to be a one-to-one correspondence. It's going to be a bijection. And a bijection is just a more formal name for a one-to-one correspondence. Bijection just means two different elements get mapped to different elements, and every element here is the image of some element here. So this function f, it's injective. If you have f of m equals f of n, that must mean that m equals n, and it must also be surjective. Let me just put a word here, injective. And it's also surjective for every n in the integers. There's going to be some natural number such that f of m equals n. Surjective. Both of these conditions combined mean that the function is bijective. It is one-to-one. And, well, let me just try to draw this correspondence here. 0, 1, -1, 2, -2. It's quite a more convoluted correspondence if I write down the sets like this. But, well, you can reason by analogy with the finite case, right? We said, yeah, there are 4 letters, A, B, C, D, because we can put them in correspondence with the numbers from 1 to 4, and it doesn't matter if that correspondence is a bit more convoluted. And in that same sense, we might say that there are as many natural numbers as there are integers. So we might ask ourselves, if we know that there are as many natural numbers as there are integers, well, how many of each are there, right? Like we can say that there are 4 different suits, so how many natural numbers are there? Well, we mathematicians have defined a symbol for this answer. We say that there are aleph 0 different natural numbers, aleph here being the Hebrew letter. And, well, what is aleph 0, you might ask? Well, that's a bit of a... Well, aleph 0 is defined to be the number of natural numbers. Of course, we'll go more into depth into that in the next video. This is just trying to be a sort of introduction. But we will be able to write that the cardinality, which is just a word for the amount, the cardinality or the amount of natural numbers, and, well, I should also mention that I'm writing the cardinality here as a hashtag symbol. The cardinality of the natural numbers is equal to aleph 0. And since we know that the natural numbers and the integers are in a one-to-one correspondence, then we also know that the cardinality of the integers is aleph 0. And now you might ask, well, what about other collections of numbers? For instance, we initially thought that the integers might be larger than natural numbers simply because, well, in a sense, one is a subset of the other, right? So what about the rational numbers, which is an even larger collection? Surely that gets us to the next cardinal? And, well, we can investigate that. I'm going to need a bit more space here on the whiteboard. So let's consider the question. We have, what are the rational numbers? The rational numbers are just the different fractions that one can write, the ratios of two different integers. So we can try to list them out. We have 0, 1, 1/2, 1/3, 2/3. Well, it's difficult to even try to list them out, right? It would seem like it would be it would seem like there would be no way to put them in correspondence with the natural numbers. That is, unless we think about it a bit harder. We can think of a rational number as a sort of pair, right? Like for instance, 2/3, we can think of it as the pair 2, 3 of numerator and denominator. And how can we think of a pair of integers? Well, one possible way to think of them might be as points on a grid, right? Let's consider here an infinite grid. I'm obviously just going to draw a small portion of it. Let's say one more row, one more column. So we have an infinite grid. Again, I'm only drawing part of it for obvious reasons. And let's say that we have column 0 here, column 1, column 2, column -1, column -2, and likewise for the rows, right? This is going to be row 0, row 1, row 2, row -1, row -2, and of course the idea is that this extends for all of the integers in both directions. So we can think of every fraction as being somewhere in this grid, right? For instance, the fraction 1/2, we would find it here. It would be at it would be at column 1, row number 2. Now, truthfully, we would also find this fraction in a lot of other places. For instance, over here we have -1 divided over -2, which is also the same as 1/2. But, well, that's a detail which we can ignore, so to speak. So how are we going to build the correspondence between natural numbers and rationals? Well, here's one way we could do it. We can start here at 0, 0, which, well, we need to point out that 0/0 isn't really a valid fraction. This is not going to work. But, again, that's something we can ignore. What we're going to do is take this grid, and we're going to go in a sort of spiral pattern, like this. We go outwards and outwards and outwards from 0. So, well, how to mathematically define this spiral, that's something which is really just details. You can try to figure this out, how to write this function which tells you what the nth coordinate in this spiral is. But the algorithm which we're going to do is, we're going to write down every new valid fraction. And, well, what I mean by that is, let's start here at a coordinate 0, 0. 0/0 is not a valid fraction. We can't divide by 0, obviously. So we're just going to skip this. Then we're going to go up here. 0/1, that's a valid fraction. We haven't written it down yet. In fact, we haven't written anything down. So we write this down, 0/1. Now we continue. -1 over 1. This is a valid fraction. We haven't written it down yet. So we simply write -1 over 1. We continue. -1 over 0. That's not a valid fraction, so we skip it. -1 over -1. That's equal to 1. That's a new fraction, so we can write it down. Let's continue. 0 over -1. Well, we have already written down 0. We wrote it down as 0 over 1. So we're going to skip this. 1 over -1. That's the same as -1, which we already wrote down, so we just skip it. 1 over 0. That's not a valid fraction. 1 over 1. We already wrote it down. Now 1 over 2. That is a new fraction. So we write it down. And we continue. 0 over 2. We already have 0. -1 over 2. That's a new fraction. We write it down. -2 over 2. That's just -1, and we already have that. -2 over 1. That's a new fraction. That's equal to -2. -2 over 0. That's not a valid fraction. -2 over -1. That's 2. That's a new fraction. I'll put it down here. -2 over -1. -2 over -2. That's just 1. We already have that. -1 over -2. That's 1/2. We already have that. And, well, I think you get the point by now. We can continue this indefinitely. And if we do this, then every fraction, every rational number, will be written down exactly once. And, well, by simply taking this as sort of enumeration, by saying this is going to go to 0, this is going to go to 1, this is going to go to 2, this is going to go to 3, and so on, this gives us a correspondence between the natural numbers and the rationals, which means that there are exactly as many rationals as there are natural numbers, which is Aleph 0. So, well, I mean, you can start to see a pattern. It would seem like every different infinite collection is just going to give us Aleph 0, right? Well, that's not true. In fact, we are going to be able to prove, and I'm going to leave this for next video because I think it's a very interesting argument. It deserves a video all on its own. We're going to be able to prove that the cardinality of the real numbers is larger than Aleph 0. What does larger mean here? Well, it means there are certainly at least Aleph 0 real numbers, right? 0, 1, 2, 3, 4. If we just take the subset of natural numbers, that already gives us a set of cardinality Aleph 0. But what's going to happen is we're going to be able to prove that there is no one-to-one correspondence between the natural numbers and the real numbers. In fact, for any function that we take from the naturals to the reals, this function can never be surjective. I'm going to put this in bold red letters. This is not going to be surjective. There's always going to be some real number that we miss. And, well, this is kind of an impressive result on its own. It means that naturals, integers, rationals, in fact, even larger collections like algebraic numbers, these are all of the same size. They're countable collections. That is, we can put them in a one-to-one correspondence with the natural numbers. And yet the real numbers are somehow larger than this. There is no way to match them up with the natural numbers. And that's quite an impressive result. So, all of this has been a bit of a preamble as to how cardinals are going to work. Again, I'm going to give many more details about this on the next video. Now, what about this other word in the title, the ordinals? What's going on with them? What are they useful for? Well, something that we have been doing so far, kind of implicitly, is equate two different notions of counting. We said the set A, B, C, D has 4 elements because we can match them up as 1, 2, 3, 4. But in that matching up, there's something else that we did. We didn't just match up the letters to some set. We specifically matched it to a set which has certain ordering, right? I mean, 1, 2, 3, 4. Just in the way that I'm saying these numbers, you can tell that there's an order to them. Specifically, the set 1, 2, 3, 4 is what's known as a linear order, where, well, we call it a linear order because everything just goes neatly in a line, right? 1, and then 2, and then 3, and then 4, and then so on. So, in the process of counting, we've been matching up sets to not just any other set, but specifically linear ordered sets. In fact, there's a stronger condition here at play, which I'll get into in the next video, but which is called a well ordering. Which basically means that in our set, it's not just that we have that every number follows the next one neatly. We have a sort of finiteness property, which, well, again, this is a more technical matter, which I will get into in the next video. It suffices to say that the natural numbers will have this property as well. And the fact that the natural numbers are well ordering means that we can use them not just for counting in the sense of size, but counting in the sense of enumeration. Where, for instance, let's consider this function that we had on the rational numbers again. It's a bit of a weird function, the one that sends 0 to 0, 1 to -1, 2 to 1, 3 to 1/2, 4 to -1/2, 5 to -2. This is a one-to-one correspondence between two sets, yes, but it also allows us to talk about the first rational number, 0, then the second rational number, -1, and then the third rational number, 1, and so on. Now, there's a bit of a subtle point here. Why am I saying first, second, third, fourth, when the numbers here are clearly offset by 1, right? Like, the first element really isn't the first element, it's the one that corresponds to 0. And, well, I think that's just an unfortunate quirk of the English language. We could very well have talked about zeroth, first, second, third. And to avoid confusion, I'll be trying to use these nth terms. Instead of writing down first and second and third, I'll simply be using nth to refer to the element which corresponds to n. So 0 here is the 0th rational number, 1 is the 1th rational number. It's a very weird convention, I know, but it will get us rid of that ambiguity that we have with the English language. And, well, the larger point to be made here is that we're not just doing an arbitrary matching of sets with sets, we're giving a sort of order structure to the rationals by doing this, right? We have 0, which is less than, -1, which is less than 1. Of course, they're not less than in the sense of, well, in the sense of rational numbers, right? This is a sort of another ordering that we're putting on the set, which doesn't really match the usual ordering. In fact, we can write it down using this other symbol. 0 is less than, with this curly less, to -1, which is less than, with this curly symbol, to 1, and so on. This is an ordering, in fact a well ordering that I'm putting on the rational numbers, and it allows us to talk about the nth rational number. Now, of course, we it makes sense to talk about the nth element in some set whenever n is finite. But what happens if n is not finite? Let's consider an example, for instance. Let us say that we have the natural numbers with their usual ordering, which is just 0, then 1, then 2, then 3, and so on. But then we append the new formal element, which we can suggestively denote as infinity. And, well, you might ask yourself, what do you mean? Infinity is not a natural number? Yeah, of course it's not. This is just another formal element that I'm appending to the set. Infinity is just going to be whatever else. I mean, really just needs to be anything that is outside of the natural numbers. And we're going to define a new ordering on this collection, such that the natural numbers have their usual ordering, and infinity is defined to be simply larger than any other natural number. That's just how we're going to define it, right? So infinity here is just a symbol, so to say. And, well, my question here is, if you want to enumerate this set, what position would infinity be in? I mean, of course, 0 is in the 0th position, 1 is in the 1th position, 2 is in the 2th position, and so on. What position is infinity in? And, well, first of all, we should notice that this is a different question than the one that we were asking when we were talking about cardinality, right? We can in fact prove that this collection of the natural numbers plus infinity, the cardinal of this collection is just L0 again. It's not very difficult to prove. In fact, you can see that this collection, for instance, if we were to map every natural number to itself, and we were to map infinity to, say, -1, then this entire collection can be neatly put inside of the integers, right? Which means that it can't be any larger than the integers. So, well, the point here is that this collection is really of the same size as the natural numbers, but it does have a different property with regards to its order, because this infinity element, it's not the first, the second, the third, the fourth, the fifth element in this sequence. It's somehow larger than all of the other elements in the sequence, right? It's in a new position. And, well, how do we describe this position? We have to introduce a new symbol. We're going to say that infinity here in this sequence is the omega element. Omega here is just the last letter of the Greek alphabet. We're going to be seeing a lot of letters from other alphabets here. And, well, you might ask, okay, but what does the omega mean here? Well, that's going to be something for a future video. Again, this is just trying to be an introduction, a lengthy introduction. But omega here is just going to describe a position within an enumeration, which is the first position which follows the 0th, the 1st, the 2nd, the 3rd, the 4th, the 5th, all of these natural number indexes. Omega is the first thing that comes after. And, well, you may then ask, what happens if we do this process again? What if we add a new infinite element? Let's, I don't know, put it as omega prime. Sorry, infinity prime. What position is this going to take? Well, it goes after the 0th, the 1st, the 2nd, the 3rd, all of these positions, but it also goes after the omega position. So, what position do we give this? We are going to say that this position is omega plus 1. And, well, maybe you can start to see the pattern here. If you had another element here, let's say infinity double prime, the position here would be omega plus 2. And if we kept going, we might have omega plus 3, omega plus 4. We might eventually get all the way to omega times 2, omega times 3, omega squared, and all sorts of other things, right? So these are the ordinal numbers. It might be apparent from the fact that I've been mentioning orderings this whole time. Ordinals comes from ordering, cardinals come from size, ordinals come from enumeration. Well, at this point, they probably seem like entirely disparate subjects. The commonality is that they both allow you to count a set in two different senses of the word count. Cardinals don't care about any of the internal structure of a set. They just care about, can you cook up some weird correspondence between these two sets or not? Meanwhile, ordinals do care about the ordering structure of a set, and they describe what positions elements take within this order within some set. Now, I could end the video here, but I do want to give a bit of an example of why you might care about these sorts of concepts, right? Because as I've described them so far, they seem like a pretty abstract tool. I mean, they let us play around with infinite collections, that's neat. But I would like to give a bit of an applied example, so to speak. Admittedly, this is going to be somewhat of a contrived problem, but it's a pretty nice problem, which, I mean, I find it nice. And the idea here is to give you a sort of real world application of these concepts. Now, I am going to be using some concepts from analysis. Specifically, I'm going to be talking about continuous functions. So, if this is some material that you're unfamiliar with, well, you don't really lose that much by just skipping the video at this point. But, I mean, if you are at least somewhat familiar with these concepts, I hope that you can see that this is a pretty interesting problem, which doesn't really have any easier solution as far as I'm aware. So let me start by just clearing this up. I need to figure out how to use the eraser eventually. And the problem that I have is the following. We're going to start with considering the Euclidean plane, that is, pairs of real numbers. So, you know, we're going to consider pairs A and B, where A and B are both real numbers. So a coordinate plane, basically. Now, the problem that I want to pose is, can I color every single point here in one of two colors? Let's say blue or yellow. Okay, maybe not yellow. Let's try a different tone of yellow. That works. So can we color every single point here? And I do mean everyone, using one of these two colors, blue, yellow, so that any path that I draw, no matter how convoluted, let me try to draw a convoluted path. No matter how convoluted I draw this path, it must pass through a blue point and also a yellow point. So, well, what do I mean by path here? I'm talking specifically about a continuous function, which goes from some interval into the Cartesian plane. This continuous assumption is important because otherwise we could just select a function which specifically takes on all of the blue points and jumps around everywhere, right? That wouldn't be any fun. We do want a continuity function. Continuous. And, well, yeah, we want our coloring to be such that No matter what kind of path we draw, no matter how small, no matter how large, no matter how twisted, it only needs to be continuous. We want it to pass through one yellow point and through one blue point. And so, well, how do we achieve this? It, in a way, it seems like most colorigs probably have this property, right? Like, if I just were to splatter around the blue points and the yellow points, and I were to do it in some way that doesn't have any specific pattern, like I don't want to leave any lines, I don't want to leave any curves, I don't want to leave anything. It just needs to be basically random, right? It would seem like if we did this randomly enough, then it would probably have the property that we want, right? If we had a collection of points which is totally random, then, well, there's no way you're going to find this a whole path that's the same color. I mean, it's kind of intuitive, right? But how do you actually prove that such a coloring exists? Now, I'm not aware of any like explicit construction. I'm not aware of any algorithm that you can do which tells you, okay, so if the coordinate of this point is of the following form, then color it blue, and otherwise color it yellow, and then this works. If there is such an algorithm, I don't know it. There might be one. I invite you to try and find one. But by using the tools of the ordinal numbers, we don't need to find one. We can simply prove that one exists. And I'm going to tell you how we do this. So the very first thing that we're going to have to do is we're going to have to count how many paths there are. And you might say, well, surely there must be a huge infinite amount of them. I mean, a path can look like this, it can look like this, it can look like this. And you might expect that surely there has to be a huge amount. But in fact, we can prove that there's only as many paths as there are real numbers. Which, I mean, it's still a huge amount, but, well, I don't know, maybe it's not as huge as you might think it is. And the reason for this is that a continuous path is determined entirely on what values it takes on rational numbers, right? Like, let's say that this interval is the interval between 0 and 1. This is just without loss of any generality. So, any function, any continuous function from this interval from 0 to 1 to the Cartesian plane is going to be defined by whichever values it takes, f of q, when q is irrational between 0 and 1. And the reason here is just continuity, right? Like, if we want to figure out what value this takes on, say, f of, I don't know, square root of 1/2, well, what we can do is we can take a sequence of rational numbers which converges to square root of 1/2. Let's say qn goes to square root of 1/2. And then by continuity, f of q, f of qn must converge to f of square root of 1/2. That is, the value of this function is just whatever this sequence converges to. And so, well, we can do some cardinal arithmetic, which again is something that we'll learn about in a future episode. We can figure out that the number of functions from the rational numbers to the pairs of real numbers, the cardinality of this collection is just going to be the cardinality of the real numbers. So that in itself is a pretty curious result. It means that there's only as many paths as there are real numbers to take care of. I mean, that doesn't seem to get us any closer to a solution initially, but what we need to do is we need to be smart about it. What we're going to do is we're going to take all of our continuous paths and we're going to enumerate them. We're going to go path number 0, path number 1, sorry, path number 2, path number 3, then we're going to continue, path number omega, path number omega plus 1, and we're going to continue way past this. In fact, we're going to go all the way until we have a real amount, until we have as many paths as we have real numbers, right? And I mean, maybe that doesn't seem to make a lot of sense at this moment. It will make more sense eventually. But the point is, we're going to have this huge infinite list which goes over all of the paths and which only stops when we get to the cardinality of the real numbers. And so what we're going to do now is the following. Let's start with, say, path 0. Path 0, let's say that it looks like this. Well, I'll draw a smaller path actually. Let's say that it looks like this. And actually, at this point we haven't really colored the plane yet, so let me just delete all of my points here. We haven't colored yet, and our goal is to define the coloring. So, let's say that we have path 0, and it looks kind of like this. So what we're going to do is, we're going to take path 0, we're going to color one of its points yellow, and one of its points blue. And we move on to path 1. We already did path 0, we move on to path 1. So let's say that path 1 looks like this. I don't know, it could look like anything. I'm going to grab 2 random points. I just need to make sure that there are 2 points that I haven't yet colored. And I'm going to color one of them blue and one of them yellow. And then I continue. Path 1 done. Now path 2. Path 2 maybe looks like this. I'm going to color one of them blue, one of them yellow. And I'm just going to continue doing this. Now, the question is, how do I know that I haven't colored, like, let's say that we're at path omega, for instance. When we're at path omega, we've already colored an infinite amount of paths by that point. Or rather, we've already colored 2 of the points and infinitely many paths at that point. So when I take path omega, which, I don't know, maybe it's this, how do I know that there's still new points that I haven't yet colored? Like, maybe path omega is already completely blue and I already failed. Well, that can't happen. And the reason that that can't happen is because path omega has as many points as there are real numbers. That's not very difficult to see. And so, as a consequence of that, by the time we get to path omega, well, how many paths have we colored? At this point we've colored path 0, path 1, path 2. We've colored 1 path for every natural number. That is, we've colored Aleph 0 paths. But there are more than Aleph 0 points on every single path. There are as many as the real numbers, and we know that the real numbers are larger than Aleph 0. So, at this point, we have not yet colored all of the points in this path. So we can choose 2 ones that we haven't colored, color one of them blue, and color one of them yellow. And we can continue. We can continue path omega plus 1, and we can go all the way until every single path has been covered. So, what will happen by the end of this? By the end of this, every single path, and I do mean every single one, will have 2 points, one of them yellow, one of them blue, and, well, if there's still any points that we haven't colored by then, we can just color all of them blue or whatever. And, well, that gives us our coloring. That works. And I mean, of course there's a lot of details that I haven't gone into here. I haven't explained why you can enumerate all of the paths like this. I haven't explained why there are only as many paths as there are real numbers. I haven't explained why this sort of weird induction thing works. That's all going to be for future videos. But, well, my point in showing you this problem was in showing you that there are in fact applications of this concept that are not just super abstract set theory. And, well, I hope to see all of you in the next video, where I'm going to basically go over the same material but with quite more formality. We're going to define with more care what it means for a set to have a certain cardinality, and we'll hopefully prove some basic theorems about that. So, see you then. Oh, and I almost forgot to mention, there's also going to be some complementary material here on the video description. I've written up a short LaTeX document which basically just summarizes what I've just said in this video. It also contains this information but in a different format if that's what you want. I'll be leaving exercises in these for future videos. I haven't really left an exercise here because, well, this is still just meant to be an introduction. But, well, I hope that you can make use of that as well. And, okay, now I'm going to go. Bye.